And we're given that the sun is a sphere with a radius 6.96 times 10 power 8 meters and an average surface temperature of 5,800 Kelvin. We want to find the amount by which the sun's thermal radiation increases the entropy of the entire universe each second. Assume that the sun is a perfect black body and that the average temperature of the rest of the universe is 2.73 Kelvin. Do not consider the thermal radiation absorbed by the sun from the rest of the universe. So, um, when we want to find the entropy of the universe, usually we write this as the sum of the entropy of some given system, which is undergoing a certain process. In this case, the system is the sun and it's undergoing some radiation heat transfer. And we have to add to this the change in entropy of the surrounding, so everything else that is in the universe. Now, looking at the process that is occurring, the change in entropy of the sun is due to some radiation energy that is released from the sun. So the general formula is Q over T, where T is that of the sun, Q is that is released by the sun. So it's going to be some negative Q, by the way. And for the surrounding will be absorbing some energy. So we write this as a positive quantity. And we have to divide this by the temperature of the surrounding, which is basically the temperature of the universe that is given to us. Now, for the value of Q, because the process is basically some heat transfer by radiation, I will write down the formula of the radiation heat transfer. We want to find the increase of the entropy each second. So I know the time is 1 second. E is the emissivity, and because we are considering the sun to be a black body, then the emissivity value is just 1. And sigma is the Stefan-Boltzmann constant, which can be written as 5.67 times 10 power minus 8. T is the temperature of the sun, which is given by 5,800 Kelvin. And A is the surface area. The surface area of the sun, since it's a sphere, can be written as 4 pi r squared. We have the radius, so we can calculate the area. Remember, when we study heat transfer, for the radiation formula, A is the surface area. Whereas if we are studying, for example, heat transfer by conduction, which is written as Ka delta T over L times T, in that case, A is the cross-sectional area. If we're studying through a sphere, this is going to be pi r squared, whereas the surface area is 4 pi r squared. If we had a cylinder, then the surface area would be 2 pi RL. This is the area of the curved surface of the cylinder, plus the areas of the two circular faces. So that can be written as 2 pi r squared. Remember, the radiation will be through all surfaces. So this is the curved face, which has an area 2 pi RL, and there is also some radiation through the top and bottom faces, which are circles of area pi r squared each. If we were studying heat transfer by conduction, then the cross-sectional area will again be the same as the sphere. It will be pi r squared, because heat is transferring through the circular face only. So back to our study, we just need to calculate Q. So Q is equal to 1 times 5.67 times 10 power minus 8 times 5,800 power 4 times 4 pi times the radius, which is given as 6.96 times 10 power 8 squared times the time, which is 1 second. So we can just calculate the answer for Q and then deduce the value for delta S. So if we calculate delta S itself, So first, the value of Q is going to be 3.9 times 10 power 26 joules. Then we can proceed to calculate delta S. So the amount of heat that is released by the sun divided by its temperature, plus this same heat is absorbed by the surrounding. And we have to divide it by the temperature of the surrounding now. And we will get delta S to be equal to 1.4 times 10 power 26 joules per Kelvin.